functions and transformations. Pause, match each function and function name to the correct graph. For example, the first graph is a straight line. Well, we know that's linear, and then the function would be f of x equals x, or we could say y equals x. Today we're going to focus on absolute value functions. Take a moment to fill in your table of values for the function y equals absolute value x, then plot your points and sketch your graph. What do you notice about your absolute value graph? It's in the shape of a V, absolute value V. Since it's in the shape of a V, it has a point to it. That point is called the vertex. Ours, in this case, is 0, 0. These graphs also have pattern points. If we start at the vertex, we can go over 1, up 1 to get our next set of points. Go back to the vertex, go over 2, up 2, back to the vertex, over 3, up 3, and so on. That'll come in handy later. Looking at this graph, there's symmetry, right? One side of the graph is symmetric to the other. So right down the middle of this graph, we have an axis of symmetry. X equals 0. Looking at some other characteristics of this graph, does it have a minimum or maximum value? What that means is we're going to look at the y values of the graph. Does the graph have an absolute maximum y value it reaches? Meaning, does the graph have a ceiling? Or does the graph have an absolute minimum y value it reaches? So does it have a floor? Our graph starts at the vertex and then shoots off to infinity. So if it had a ceiling, it breaks right through it. So this graph does not have a maximum y value, it has a minimum y value. So we would say minimum value of 0 at x equals 0, because our vertex is a 0, 0. Now let's look at domain and range. Domain of a function is the set of all input values, x values, for which the function is defined. On a graph, it helps if we picture ourselves on the x-axis. Let's start on the left side of the x-axis. If I look up and down on the left side of the x-axis and I can see the graph, then that's included in my domain. So as I walk across the x-axis, I can see the graph all the way across. So that means all real numbers are included in my domain. We could list this in a different way, called interval notation. Again, on the left side of my graph, I look up, I can see graph. That part of the graph goes all the way to negative infinity. So we say negative infinity, I can see the graph all the way across to the other side to positive infinity. Now range is the set of all output values or y values for which the function is defined. So now I'm going to put myself on the y-axis all the way at the bottom. Down here, if I look left and I look right, I don't see any graph. Where am I going to see graph for the first time? As I climb up, the very first place I see graph is at 0. And then if I climb up past 0, everywhere after 0, I'm going to be seeing graph to the left and right of me. So my range is going to be from 0 all the way up to infinity. Well, that means my range is y greater than or equal to 0. Now, if I list in interval notation, I would have to say, okay, right at 0 is where I see the graph. So we use a bracket to say that we're equal to that 0, and then everything up past that, we never actually can reach infinity, so we use a parentheses around infinity instead of a bracket. 0 to infinity.
Now let's look at some transformations to our parent function. We see g of x equals negative absolute value of x. What do you think is going to happen? Well, let's plug in negative 2. Negative absolute value, negative 2. Well, then that's going to end up being a negative 1 times positive 2, so it's negative 2. What would happen if we plugged in that positive 2? Well, negative absolute value of positive 2. Once again, we have the value negative 2. Take a look at negative 1 and 1. We also get negative 1 as the output for both, and then of course 0, 0. Let's plot our points and see what's happened to the graph. Well, that's interesting. The graph has reflected in the x-axis. The y values have been multiplied by a negative 1. Now let's take a look at h of x. We have the absolute value of x and then subtract 3. What's going to happen to our graph? Well, let's do our table of values, graph it, and see. Plug in negative 2. So h of negative 2, absolute value of negative 2 is positive 2, minus 3, negative 1. What about h of 2? Same idea. positive 2, minus 3, negative 1. Finish the table of values, plot the points, and graph to see what's happened. So what happened? It looks like our parent function has been translated down 3 units. When we consider the table of values from the parent function to our translated function, all of the y values have decreased by 3. Okay, we've seen a couple of transformations now. Look at this next one. We have the absolute value, and inside that is x minus 3. Do you want to take a guess now? What's going to happen to our parent function? Well, you might notice that we've renumbered our table of values because, of course, I have an idea what's going to happen. So the first value we plug in is 1. Absolute value of 1 minus 3. Well, that's negative 2, but absolute value, always positive, is 2. Then plug in 2 and so on. Finish that table of values, plot the point, and sketch to see what's happened. What? The absolute value graph has translated which direction? To the right 3 units? But it was a minus 3. I would have thought it moved to the left. We're going to have to take a look at this. On the parent function for the x values, we've been using negative 2, negative 1, 0, 1, 2. Well, I had changed it to 1, 2, 3, 4, 5. Why? Well, I knew that negative 2 plus 3 gives me 1. Negative 1 plus 3, I'm at 2. I knew that x values were going to increase by 3 and the y values were going to stay the same. So we've looked at a couple of transformations so far. One is a translation. That's a shift up, down, or left, right. We've also seen a reflection where the y values were multiplied by negative 1. Later on, we're going to see that we can also have a reflection when the x values are multiplied by negative 1. Visually, the graph flips. Now, the last transformation is a dilation, and we haven't seen that one yet. A dilation changes the size or shape of the original graph.
Let's practice a bit with what we know about transformations. G of x equals absolute value of x plus 3. Well, hey, we just did one like this. What do you think a plus 3 inside my absolute value bar is going to do? Did you guess translated left 3? You'd be right. If minus on the inside of my absolute values is to the right, plus is to the left. To sketch the graph here, I don't want to make a whole table of values again. Since I know it's translated to the left 3, I could use my pattern points to sketch this graph. The parent function's vertex starts at 0, 0. Well, translate to the left 3. Then from there, I can just go over 1, up 1, back to the vertex, over 2, up 2, back to the vertex, over 3, up 3, and so on. Now, let's identify some characteristics. We know the vertex is at negative 3, 0. So that means the axis of symmetry is at x equals negative 3. It's always going to match the x value of our vertex. Does this one have a minimum or maximum value? Is there a ceiling or a floor? There's a floor, so there's a minimum y value here. Looks like it's 0. That's the y value of my vertex, and it occurs at x equals negative 3. Domain and range. Okay, domain, x values. We're going to be on the x-axis. I can see the graph all the way across the x-axis, so all real numbers. Now for the range, y-axis. I put myself at the bottom of the y-axis. I look left, I look right, I don't see any graph. As I climb up, I get to that x-axis. I look to the left and there's graph. So the range starts at 0 and then I can see the graph everywhere after that. So y is greater than or equal to 0 or 0 to infinity.
Look at this next one. We have 2 translations. That's going to be fun. Okay, inside with the x, I see x minus 2. And remember, inside is kind of opposite. Minus 2 makes me think left, but it's actually right. Outside, the minus 3, that one's same because it does go down 3. Now, once again, we're going to use our pattern points. I don't need a table of values. Where's that vertex going to be? Instead of 0, 0, I go to the right 2 units and then down 3. From the new vertex, over 1, up 1, back to the vertex, over 2, up 2, back to the vertex, over 3, up 3. Now vertex, well, we went to the right 2 and down 3, so the new vertex is at the point 2, negative 3. The axis of symmetry is that x coordinate, so x equals 2. And then min or max value. Well, it's opening up, so I know I have a floor. So the min value of -3 at x equals 2. Domain hasn't changed. It's still all real numbers. But now the range has, because that graph has moved down 3 units. So when Miss Ryan is crawling up the y-axis looking left and right, the first time she's going to see part of the graph is at y equals -3. So the range will be y greater than or equal to -3.
J of x. This time we have 3 transformations. What's that negative outside the absolute value gonna do? It's a reflection over the x-axis. Now how about that +1 inside and that +2 outside? See if you can write them down. Inside opposite, so +1 is left 1, outside same, so +2 is up 2, and that's the location of our vertex. From there, I do my pattern points, over 1, up 1. Wait, I'm reflected this time. So back to my vertex, over 1, down 1. Back to my vertex, over 2, down 2. Back to my vertex, over 3, down 3. Vertex, -1, 2, axis of symmetry, x equals -1. Min or maximum value? Does my graph have a ceiling or a floor? Wait a minute, this time I have a ceiling. I have an absolute max y value of 2 at x equals -1. Domain, it's not gonna change. We're still all real numbers here, but my range is different. When I'm sitting at the bottom of my y-axis this time, I look left and right, I can actually see the graph. Where do I stop seeing the graph as I climb up the y-axis? At that max value of 2. So my range is all y values less than or equal to 2.
Let's formalize our notation. Given the graph y equals f of x, horizontal translations. Okay, f of x minus h, and of course that's inside with the x, so opposite. That means we'll translate to the right h units. Next one, f of x plus h, inside opposite, translate to the left h units. Looking at vertical translations, now we have f of x, close that parentheses, and then plus k. Well, now, outside same, we're going to translate up k units, and of course, the minus k will translate down k units. Okay, let's practice writing function rules. We're given an equation. We need to identify a parent function. What's a parent function? Well, let's go back and think about our function families. Which function family does this belong to? I see an x squared. Well, that was a quadratic function family. So let's go ahead and name our parent function f of x equals x squared. Now, what are the transformations? Well, I see the +5. That means it's been translated up 5 units. Now last, let's go ahead and write a function rule based off of our parent function. So g of x equals f of x, the parent function, +5. Let's take a look at b. Which function family is this part of? Square root. Okay, so let's name our parent function. F of x equals the square root of x. Now, x minus 1 is inside with the x, so that means it's been translated to the right 1 unit. Now for the function rule. G of x equals f of, this has to be inside with the x, so f of x minus 1. All right, there's 2 more. Let's see how much of those you can get. Even if it's only part of it, give it a try. Pause. All right, did you identify that parent function as the quadratic? And then let's do our function rule. Check it. G of x equals f of x minus 2 and then minus 4 outside. The next, our parent function is the absolute value function. F of x equals absolute value of x. And our function rule, it's been translated up 7, is simply g of x equals 7 plus f of x. Or, commutative property of addition, f of x plus 7.
Let's write some function rules for graphs. If the solid line graph is my parent function, that's f of x, what's the parent function for this first graph? It's an absolute value graph, right? F of x equals absolute value x. Now the dashed line graph is going to be my g of x, my transformed graph. I want to write a function rule for g of x in terms of my parent function. Well, it looks like my v flipped upside down, so I know it's reflected over the x-axis. What else changed? Well, I translated to the left 2 units. So g of x equals negative, because of my reflection, f of x, I moved to the left, so inside x minus 2. Oh, wait, inside opposite, so x plus 2. And hey, since I know the parent function for this graph, I could actually write an equation for g of x. G of x equals negative absolute value x plus 2. Which function family is this graph a part of? The square root graph. So f of x equals the square root of x. Now, what transformations occurred to get me to the graph of g of x? Well, looks like it translated to the right 3 and down 3. G of x equals f of x minus 3, close parenthesis, minus 3. So if I wanted to write an equation for this graph, g of x equals the square root of x minus 3 inside my square root minus 3 outside. Does this last one match any of our function families? Not that we've seen so far. It looks like a quartic to me, but for now, we'll call it y equals f of x. Now to figure out the transformations to get to g of x, well, let's just try to track a point. If I start right here, it looks like I move to the left 4 and up 5. Let's track this one. Okay, left 4 and up 5. All right, I'm feeling good about this. Our function rule will be g of x equals f of x plus 4 inside plus 5 outside. And since we don't know the parent function, we can't write an equation for the graph.